The clique, also known as the clique of a graph, is some subgraph of G, which is also a complete graph on those vertices. In other words, it's a complete subgraph. Now, we care about maximum cliques or maximum cliques, and these are the complete subgraphs or a complete subgraph that has the most number of vertices possible. So the official term here would be maximum order or greatest order if you prefer. And remember, order was dealing with the number of vertices. Now, this guy with the little w, that actually counts the number of vertices in your maximum clique, okay? Sometimes referred to as your maximal clique. But it's the number of vertices in that complete subgraph that has the most number of vertices. So you count up the number of vertices. So for example, if this maximum clique was K3, the W here would be the 3. Okay. In terms of writing them out, you will often see it written as, and this is not scrolling on me. All right, there we go. In terms of how they're written, your cliques are typically not written with the K and then the subscript, although we totally did that last time just fine. They'll often be written as the 1 clique, the 2 clique, the 3 clique, the 4 clique, and this number, the 1 through 4 right there, is telling you how many vertices are involved. So this omega of G refers to, or would be, this number in front of the dash of the largest clique that's in your graph possible. Okay, so that would be the crash course in terms of that omega of G. In other words, it's the maximum, the order of the maximum clique. Now, the other things that we looked at were colorings. So if you talk about the coloring of a graph, it's always referring to your vertices. The colorings are often called K colorings. The K here would refer to how many colors you actually ended up using. Okay, so in a question, maybe it'll say something like find a 2 coloring. Well, that would only work if you were only able to use 2 colors in your graph. If it says find a 5 coloring, the question there is asking you to use 5 colors when you color up your vertices. Okay. Yes, we mentioned that just a second ago. We're going to cover the chromatic polynomials when we get to section 2.4. Okay. Our chromatic number then is the number of colors that you use, but it's not any old number of colors you use. This is the fewest colors that you use, or the minimum number that you would use. Okay, and this is that fancy symbol that's the Greek letter chi in front of it. Okay, and here's the interplay between the omega of G that we talked about with the size of the cliques, or really the order of the cliques, and that would be the smallest your minimum number of colors is that you could ever use. So the smallest your chromatic number could ever be, and the largest your chromatic number would ever be would be the number of vertices. So in terms of formulas for chromatic numbers, this is where your chromatic polynomial comes into play. So it turns out there are formulas, well, it's really more of an algorithm to get your chromatic polynomial. And then once you have your chromatic polynomial, then you can use it sort of as a formula for your chromatic number. Right now, based on what we've done, we've built the formulas for the chromatic number for several different types of graphs. But honestly, it's in terms of your chromatic number, right now, it is a lot of just looking at it. It's also each graph has its own number, and it's not like the graph itself is going to have different chromatic numbers. There's exactly one chromatic number per graph. So one of the things you do if you've ever looked on either the math dictionary that we showed just a second ago, or if you look on Wikipedia, they'll actually give you charts, and they'll list out the names of famous graphs. And in the chart, one of the things that they'll do is they'll actually say, hey, this guy has the chromatic number of, and then it gives you whatever the chromatic number is. Okay. But that is one of the things that people have done a lot of work on, is actually figuring out the chromatic number of. It's not necessarily a lot of work on the one graph, but like a lot of work on a whole family of graphs or a bunch of different graphs. But I digress a little bit. All right, so there's this inequality. Now, in terms of what we're going to do today to finish up section 2.3, we are going to look at, we'll end at sort of an application of coloring, but what I wanted to do is 2 big things. One is we'll look at another example where we try to find the chromatic number of a graph. This is actually the Peterson graph, which is a famous graph. It has, notice, It looks kind of like a pentagon on the outside, and on the inside it looks like a star, so it's got like 2 layers, if you will. Okay. Then the other big thing that we do, and this is really the one big thing that we've missed or that we didn't get to yesterday in terms of section 2.3, we want to look at edge chromatic numbers, which is if you color your graph but you're not focusing in on coloring the vertices, you're focusing in on coloring the edges. So we're going to look at that too. Okay. Once we're done with that, we'll move on to section 2.4 and get into all of the formulas and the properties and the chromatic polynomials. So in terms of how your book is structured, 2.3 is like doing bunches of examples, and 2.4 is now like the theory and the formulas, which is why we haven't had too many formulas yet. Okay. All right, so if we look at this Peterson graph, and suppose we want to go ahead and color this graph. Well, let's be a little bit strategic about this. First thing is let's make sure my pen is actually going to draw if I write with it. So first thing that you want to do, and you don't actually have to write this down, but I'll write it to the side just so we're all on the same page, is look at how many vertices you have, look at how many edges you have. With coloring, that may or may not be super helpful, but it's always nice to have like a starting point. With colorings, it's actually more helpful to start looking at your degrees. Okay? So we'll look at those 3 things first, and then we'll start looking at our clicks and see if we can find a maximum click. Okay? So for this guy, if we look at the vertices, we saw we had 2 layers, this sort of pentagonal shaped layer and this sort of star shaped layer, and it looks like there's 5 vertices in each, so that looks like what? 10 vertices total. Now if we then look at the edges, I want to say there's 15. Let's check. 1, 2, 3, 4, 5 in that 5 cycle. We've then got the star, so 1, 2, that looks like 5 in this little star right there. And then we've got 1, 2, 3, 4, 5 connecting between the 2 layers. So yes, that looks like 15. Excellent, you guys got the same count. So then we look at degrees. So if you look at all your vertices, what degrees are we going to be looking at with the different vertices of this graph? Yeah, they look like all degree 3 to me as well. So this is for all vertices. Now, what does that mean in terms of our clicks? Okay. Well, we definitely know we have a 1 click and we have a 2 click in the graph, because remember, a 1 click, or if you prefer, K1 is just vertices. We have vertices in the graph. A 2 click, or if you prefer, K2 says you have to have at least 1 edge. So we're good there too. So then we're going to be looking at the next clicks, okay? Now technically, based on the number of vertices, which is 10, we could go all the way up to a 10 click, but in reality that's not going to happen. Notice we have only degree 3 for our vertices, and degree 3 is only up to K4. K4 has all of its vertices degree 3, so this means in terms of potential clicks, we only have up to a 4 click is possible based off of that degree. We don't need an S there. Okay? And remember, when we say click here, that is really referring to our complete graph on 3 and then 4 vertices. Okay? Now, I would recommend always doing them in order, because remember what we talked about last time. These, if you have a larger click, you always have all of these smaller clicks embedded inside of that larger subgraph. So if you check and the 3 click doesn't exist, the 4 click will automatically not exist. You don't even have to check it. So remember, 3 clicks looked roughly like what? Anybody remember? This was, we were trying to find a copy of K3. Yeah, it looked like triangles. So what do you guys see? Do you see anything that looks like a triangle the way these edges are put together in this Peterson graph? Yeah, I don't either. It turns out if you want to find the omega g, in other words, your max click size, this one doesn't even have any triangles, so that means there is no 3 click whatsoever. Don't even bother checking for a 4 click because it's not there. Now, put all this information together, that tells you that omega of g has to equal what? You guys got it. It's got to equal 2. Now, what's useful about that? Well, that gives you your inequality over here. Now, often your coloring, in other words, your chromatic number, is really close to your maximum click size. So if I was looking at this and had never attempted to color the Peterson graph ever before, which is live, I typically have this graph in this section every time I've taught the course. But for sure, the first time I tried to color it, I was like, you know what? Maybe I can actually color it in 2 colors. But even if I'd never attempted it, it would probably be, even if it doesn't use 2 colors, we probably could get it into either 3 or 4 colors. So it's normally really, your chromatic number is normally really close to your click size. And when you guys were referencing formulas, this is one of the reasons why we care about this omega of G. And I think your textbook doesn't talk about it, or at least with terms of symbols. But one of the reasons I put this in there is because it gives you a starting point for a guess of how many colors you're going to need to use. So this here tells us we should shoot for trying to use 2 colors to color this graph. And if we can't make it work, no big deal. Maybe we really do have to use the 3 or the 4 colors. Okay? So let's apply this inequality, and mainly that's so I can scroll up. If we apply that inequality, here's what we know. We know that our chromatic number is going to be somewhere between 2 and 10, but realistically it's probably going to be closer to 2. Okay. Now, if we actually go and try to start coloring, for these guys I prepped up and actually made these little open circles here. That way when we colored it, it looked like the vertices themselves were originally the color. Okay. So you start off with whatever color you want. Maybe you pick on, oh, I don't know, maybe we pick on yellow because that was the first one. So if we're super lazy, maybe we color vertex A yellow. Well, what does that tell you then? Could we then start coloring other vertices? So strategically, what other vertices might we think about coloring next? Yeah, that is exactly what I would recommend. So the next thing I would recommend is pick up a different color. And even though you can totally use filled in vertex, not filled in vertex for your 2 colors, I would definitely recommend actually doing it with 2 different colors if humanly possible, even if it's only something like you pulled out a highlighter or you pulled out a black ink pen versus a blue ink pen. Okay? So all of the vertices adjacent to A need to be a different color, and just make sure those vertices that are adjacent to A are not themselves adjacent to each other. So B, F, not adjacent to B, and then E, also not adjacent to F. Now, remember, we're trying to color this graph with as few colors as humanly possible. So, what should we do next? Anybody have a guess? Which vertex would you guys like to deal with next? G and J? Okay, we can go back to yellow. That would be smart. So if we want to use as few colors as humanly possible, we definitely want to go back to yellow. I've got a bunch of different people doing guesses or suggestions. I'm going to go with the one vertex that's in common. Actually, I'd prefer to go around the outside, but we can start here with this guy G. Okay. Now, once you deal with G, where should we go next? Yeah? See, yeah, H could be. You could actually go with H if you wanted to. I personally would probably be a little bit hesitant about H. We do have one of its vertices, one of the vertices adjacent to H already colored, so that is an okay one to deal with next, so we could go there. I would just be worried about it coming over here to C, but let's go ahead. We can color this guy yellow. You said D. D could also be colored yellow. Now, we've got 3 vertices left to color. You could, but of those 3 vertices, you want to color them either yellow or blue. Can any of those vertices be colored either yellow or blue? Since we use yellow and blue so far. The answer is, it looks like yes until you look closer. So J, no, because it's adjacent to a yellow and a blue vertex. C, no, because it's adjacent to a yellow and a blue vertex. And I know I pointed to the wrong one and said the wrong color. And I, looks like you're good here for blue, and then don't forget you've got the F there. So you do have to pick up a 3rd color for these guys. Now, here's the question. Did we actually color everything strategically? Can we use the same color for those 3 uncolored vertices right now? And the answer is yes, because as soon as you color in here C, that's also C is not adjacent to I, and I is not adjacent to F, and not F, J. So all three of those can actually be colored the same color. So that is very nice. Now, when we looked at that guy originally, there was no triangle in the graph. Okay, so that meant there was no copy of the complete graph on 3 vertices. There was no copy of K3. But notice what happened here. We still ended up getting into this situation where you had to have 2 different colored vertices were adjacent to the very same vertex right here. Another way to know for sure that you're going to have to use at least 3 colors is around the outside we have this subgraph that's a copy of the cycle graph with 5 vertices. And what do we find out with a cycle graph? We could alternate your colors, whatever the blue, that the vertex had to be a new color. Okay. So the fact that we had a subgraph of these outer 5 vertices that was C5, and we saw last time that had a chromatic number of 3, that actually meant we knew that this lower bound really was going to be a 3. Now, good news, we were actually able to find 3 colors, so that tells us what? That does tell us, hey, our chromatic number right here for this Peterson graph, I think the Peterson graph actually has a symbol P, but I'm going to do G because I would have to look that one up, would actually be 3. Now, here's the question for you. If you had this graph, could you color it with 4 colors? What do you guys think? It'd actually be way easier to color it with 4 colors because you wouldn't have to worry about things as much. Could you color this graph with 7 colors? Yeah. You could actually color it all the way up to 10 colors if you want. If you wanted to use 11 colors, that would be difficult because at least one of those colors wouldn't be used. But as one of you said, that's while you can do that, that's not the chromatic number because the chromatic number is literally telling the person, hey, this is the fewest number of colors that you could possibly use to color this graph. Now, there's definitely advantages of dealing with a chromatic number. One of the things that these guys are used for is applications, and the coloring is like some specification that or criteria that you need met in whatever. I'm going to use the word story problem or situation that you have, and this would be a way of identifying, hey, I need this criteria matched. Cool. I was able to do it with only 3 different situations. And especially if you're dealing with something you have to pay money for, having the smallest chromatic number, if that corresponds to something that you would have to purchase, is something that people look at. And I realized I was super vague with all of that, mainly because we haven't gotten into any of those examples yet. Okay. All right, so that would be the Peterson graph. And we'll actually look at the Peterson graph in a little bit when we look at edge colorings as well. All right, now we actually talked about K colorings before. I put it in the definition of a coloring, but going ahead and popping it out on its own, if you talk about a K coloring of a graph, this is simply a graph that's been colored on its vertex with K colors. And notice in terms of the number of colors that you're allowed to use, this is exactly the same thing as what we were just talking about. You can use up to the number of colors. It's the same as your number of vertices, but your chromatic number is the smallest coloring that you can actually do. So that was what we had just talked about. All right, so the next question that we have here is, what do you think? Is it possible to find a graph that could have simply a 1 coloring? And before you shout out your answers, I'm going to let all of you guys try to answer this. I actually pushed this into one of those poll everywhere questions. So I went ahead and shared this with you in case you didn't have the way to get it. So that right there is the URL, same one as always. If you've already got it on an app on your phone, it's the same one you've used before. So I'll let you guys see if you have a guess of whether it's possible to find a graph that could have a 1 coloring. Okay. And since it's the same question as right over here, I am going to hide one of them real quick. There, that way you can see the whole wording. So, key thing to know with a one coloring is you are able to color your graph with exactly one color, okay? Now, what does that tell you? Move this cursor so you can see it. What does that tell you about your chromatic number? Any guesses? If you're able to have a one coloring in your graph, what does the chromatic number have to be? Yeah, your chromatic number would have to be 1. Now, remember the inequality between your chromatic number and your maximum click size. So if your chromatic number is 1, your maximum click size would have to be what? It would also have to be 1 because what happens? In terms of your maximum click size, it has to be, it's always less than or equal to your chromatic number. So this is referring to the fact that your maximum click is 1 and your chromatic number is 1. Now, what does it mean to have a maximum click of 1? Well, a maximum click of 1 means you have a 1 click. And what did a 1 click mean you had visually in the graph? It means you had vertices, at least one of them, but if that's your maximum guy, it means you have to have no coloring graph. So, see if you think this is a possibility for a graph. And I'm going to box the graph just because there's no edges in it. So is that an example of a graph that could be colored with one color? Yeah. So that's the one that many of you guys suggested, exactly one vertex. Now, here's a second example. So it's a different graph. I'm going to box it as well. Is this an example of a graph that could be colored with one color? Yeah, actually. So it turns out if you have a graph that is able to be colored with one color, it can have as many vertices as it wants. However, it turns out you're not allowed to have any edges. So the only graphs that have a one coloring in them are graphs that have no edges. Now, if you actually do have edges, is it possible to only have a two coloring? And the answer is also yes. Okay. So I'm going to sneak that question in here right below. So let me put this in red. Wow. Let's pretend I could spell the word is. Start over there. So is it possible to have a two coloring? I think we've actually already had examples of these guys. But let me go ahead and draw some potential examples here. Here's an A, here's a B. Maybe you color in one of them, maybe you shade in A, maybe you leave A unfilled. Often when you do this shaded in and not shaded in, even though if you're using a black pen like I am, and a white background or white paper, it looks black and white. Typically, and you guys will love this, it is often actually referred to as red and blue. It's a thing. It happens. Not always. Some people really do stick with the black and white, or they stick with shaded versus unshaded, but it is really common if you ever start reading things about colorings of graphs to see them saying red and blue. I don't know. Maybe the first guys who did it really like to color red and blue. All right, so this guy here, what do you think? Does that look like it is a two coloring? And let me put a box around this. I'll do a dotted line since we actually have edges here. So that would be our graph. So this guy is an example of a two coloring. Notice it is also a disconnected graph, and purpose here threw in the disconnected graph simply because you can color any graph disconnected, connected, planar, not planar. And if we actually went ahead and did some of the specifications here, notice what happens. We had what? We had 6 vertices. We were able to color it with 2 colors. And if you looked for your omega, you looked for your maximum click. Notice here, it is also the 2 right there. As soon as you have edges, you're guaranteed to have this omega of G to be 2. And if you actually have a 2 coloring, this is where those two guys would have to match. Now, that is a lead-in for the next question. Okay? And the lead-in for the next question is dealing with what happens if you want to color a bipartite graph. Okay? Now, I have a picture of a sample bipartite graph here that I'm about to show us. But before I show you the picture of the bipartite graph, what do you guys think? How many colors, I should rephrase, what do you think the fewest number of colors is that you could color your bipartite graph? And as you guys are guessing, let me go ahead and pull up the picture of the bipartite graph. Remember, it looks like that. Now, the hallmark of the bipartite graph was what? It has however many vertices it has. So vertices, I have no idea because we put dot, dot, dots. Edges, it has at least one, so it doesn't have a one coloring. Again, don't know how many, and I don't care. But we did divide it into two groups, which is half of the hallmark of the bipartite group. What's the second condition? You've got you've got two groups of vertices. What's the thing that you have to know about the edges with respect to those vertices? Namely, where do the edges live? One endpoint of all your edges has to live where? And the other endpoint of all your edges has to live where? There we go. Yep, so that's the key criteria here is you're not allowed to have any edge that both starts and stops or has both of its endpoints in the same vertex set. So here if we label them set X and set Y, which is what we did in the past, you're not allowed to have any edge that has both of its endpoints in one of those two sets, either X or Y. Now, we also know that every cycle in a bipartite graph is length even, as you have to cross to the other set and then come back. So what that tells you here is what? You're not going to be able to have a copy of you're not going to be able to have a 3-click because K3 is what? It looks like a triangle, so that's the same thing as a cycle of length 3. So that means the best we got here is edges, or the omega of G is 2. Now you guys have already guessed how many colors that we can use, or specifically the fewest number of colors that we can use, and you guys are totally right. It turns out that the chromatic number of any bipartite graph is 2, and that's because, which is what you guys were already starting to say, color all of the vertices in one of the sets, one color, and color all of the vertices in the other set, the other color. This is actually also a way to identify if you have a bipartite graph, if you can get a 2 coloring. So let me write this property. So note, if your graph, so if G has a 2 coloring, this tells you that your graph G is bipartite. Anybody have a guess how you should divide up the those vertices? You got it. Just divide them up by your colors. So whichever one you colored, whichever vertices you colored with whichever color it was, put it on one of the sets, and all the other vertices of all the other colors on the other one. Okay. It may feel a little more intuitive, mainly because when we were dealing with the bipartite graphs, I actually colored the vertices for you. And part of that was simply because we weren't face-to-face, so you couldn't see me pointing at anything. And part of it was actually foreshadowing this property right here. So maybe if I hadn't done it, it wouldn't feel as intuitive. I don't know. But I agree. I personally find when I'm looking for bipartite graphs, if I throw colors in play there as well, I find it easier to figure out if they're bipartite as well, especially if it's just a tangled, snarled mess. Okay. All right, so that dealt with the thing about bipartite graphs, and in terms of vertex coloring, we will come back to it, but for a little bit, I want to go and talk about edge coloring. So any questions with regular old coloring before we move on to edge coloring? And just as a note, in terms of terminology, if you say coloring, you're always talking about the vertices. If you want to color your edges, you have to put that new adjective in front and actually say edge coloring. All right, so the definition of an edge coloring of a graph goes as follows. You're going to color the edges, so your edges get colored now. And the way you color the edges is if two edges are going to be incident to the same vertex, in other words, the two edges share an endpoint, then those edges have to be different colors, okay? So remember, in a regular old coloring, vertices are different colors if they're adjacent. Now, edges are different colors if they're incident. And remember, incident is where they're almost like physically touching. Now, just like we have the chromatic number with regular colorings, we're going to have an edge chromatic number as well. And the symbol is almost exactly the same. It looks exactly like the chromatic number symbol, except there's a line up top. You could actually use clicks, but with edge coloring, people typically use degrees instead. And I'll show you the degree trick that we typically use with edge coloring. But yes, if you go specifically to the omega of G with respect to vertices, that one is looking at, well, it doesn't tell you everything, but it gets you close. It's talking about how many colors are sort of all really close to each other. All right, so edge coloring, the edge chromatic number, which is, my mouse went away, which is this guy right here. So let's look at an example, and the example I pulled up for us was that same Peterson graph that we had before. So I just copied the graph from above, attempting to do, oh, I think you guys will be fine. All right, so we want to find the edge chromatic number of this graph. So let me actually put those directions in here. So find the edge chromatic number of this graph. And remember what that means. We want the fewest number of colors specifically used to color the edges. Okay. Now, the trick in terms of edge colorings is you want to identify your vertex that has the highest degree. So let me first draw a picture of what we're looking for. Okay. So in our edge coloring, and this is actually true of any edge coloring, you've got some vertex, whatever vertex it would be, and you've got your edges coming in. And yep, we found the degree of all of these guys was degree 3. So I'll go ahead and do degree 3 here. Although if you had more edges in a different graph, maybe you want to put in more edges. So if you want to color these guys, when you color the edges, you color one of them maybe yellow because that was the first thing I picked. You color the second one some color that's not yellow. I picked blue just because it was the next one in line. And the third one you pick needs to be some third color. Okay? You don't color the vertices here. Technically, you can color both the vertices and the edges, but we're not going to do that in this course because it's just craziness. Okay. Now, notice what property this actually means. In terms of when you're looking at your edge chromatic number, in other words, the fewest number of colors that you could possibly use to color your vertices, worst case scenario, color each edge differently. Please don't really do that. That is not going to give you the fewest number of colors. But what's your lower bound? What's the absolute positive before you even actually look to see how the edges are connected? Smallest number that you could get. So this would be analogous to that omega of G when we're dealing with a coloring of vertices. That would be the degree of your vertices. Now, in our case, all of our degrees are the same. So for us, 3 would be the fewest colors we're allowed to use. But in general, it's actually the largest degree you have in your graph. Okay? So if we go ahead and apply this to what we have, all of our degrees are degree 3. So this tells us that our edge chromatic number is going to be somewhere between 3 and, let's actually put the information that we had previously. Previously, we found that there were 10 vertices, 15 edges, and all of our vertices had degree 3, and that was for all of our vertices. So if we go ahead and find the number of edges, that's 15. So in terms of the colors that you could potentially use here to edge color this particular Peterson graph, we're looking at somewhere in the range between 3 and 15. If you tell me the answer is 17, I will know you're wrong without even looking at how you colored your graph. Why? Because there's not 17 edges in the graph. And if you told me that you could color this with only 2 colors on your edges, I would also know automatically that you're totally and completely wrong or did something wrong, because there's no way you could do that. You've got a degree 3 vertex in the graph. Okay? Now, what is the actual edge chromatic number? We'll find it. It's often somewhere close to whatever the maximum degree in your graph is, but unlike with when you're coloring vertices, and it's really, really common that the chromatic number is exactly the same as that omega of G, with edge colorings, it's a little bit more frequent that your edge chromatic number is 1 or 2 higher than your maximum degree, just because it all depends on how those edges are actually connected. So that was tons of extra expedited than what we probably needed. Let's actually color this thing. So which vertex do you want me to start with? And I know we're not going to color the vertex, but we'll do all the edges around that vertex. A, cool. So A is degree 3. So we'll color these guys 3 different colors. And since we're going to be coloring it a lot, let me go ahead and pin that up here. So we can grab yellow, maybe is this top one. Maybe the blue is this middle one right here. And remember, we're shooting to try to color this with 3 colors. And because I really don't like that green, let's do this horrible purple. I don't like the green just because when I wobble and overlap the yellow and blue, it actually turns into that green. Okay, so that's the only reason I chose that. Now, once we've got those 3 colors done, then we can move on to a next vertex. Horrible purple, really? Nice. Okay, so when we look at the other vertices, there is a smart way and a less than smart way of picking the next vertex to focus on. Who do you guys think would be a smart vertex to focus on next? I agree. So a smart vertex to focus on next is any vertex that already has one of its edges colored. Why? Because if you went over here and looked at, say, vertex C or D, you could still pick the same 3 or however many colors, but if you don't watch out, it may not connect back to your other guy's right, and instead of getting the edge chromatic number, maybe you color your graph just fine, but it's a little bit too many colors. Okay? So why don't we grab B, because that's the one that a couple of you guys sent in. So at vertex B, we're not going to color vertex B, but the 3 edges, well, one of them is already colored with yellow, so we'll try to use the blue and the purple here next. Okay? So we look at these guys and we say, well, all right, well, none of these guys are adjacent back to F or E, so it looks like we'll be able to use any color that we want, we hope. So let's hope we pick right. So maybe we color B to G blue. Maybe we color the B to C, that other color. Okay? And there we cross our fingers and hope everything works out. Okay? Now, anybody have a favorite vertex to focus on next? E. We could. I might recommend here try focusing in on F and G, although you could totally do E or C as well, but just pick between those 4. Anybody have a guess why I might suggest F and G? Part of it they've already have one of their edges being colored, so this is why I was pointing out C, G, F, and E, because one of their edges are colored. Focusing in on this inside bit here, the F and the G is, notice how F is going to come down here to E, going through G through J to E, and then F through H to C. We're going to have to start worrying about these edges as well. So if we can start getting some of the inside stuff edge colored, that might help us to make sure there's no issues on the outside here. Okay, so it looked like nobody talked about G, so somebody referred to F, so let's pick on F right here. Now notice where F goes. F is going to go to H or I. We can't use blue, so we can only use yellow or that purpley color. So if we color these guys, let's see. I don't see an issue right now of dealing with either of them in either sense, but maybe we do something like, I don't know, maybe purple here. Maybe that would be strategic. And if we did that one with that weirdo purple color, that means we have to do yellow from F to I. All right, now, we're now at the point where we're starting to get close to being able to join up, okay? Now, notice here if we look at H and C, we look at H and C, can we actually color the edge between H and C something that's allowable? And when I say allowable, you don't have two edges coming into the same vertex with the same color. Yeah, we could use blue. That seems a reasonable guess here. Like I didn't select blue. Okay. Now, once you go ahead and select the CH edge to be blue, what does that force you to do with this edge right here, C to D? It has to be yellow, exactly. And now we've got several vertices that their edges are partially colored. We've got the vertex G, which still has only one edge that's covered. We've got the vertex H that has two edges incident to him colored. And we've got D and I, which have one edge incident to them colored. So I would definitely, if I was doing this on my own, I would be looking at edge HJ, and I would also be looking at the edge here ID, would be the two edges I'd be really focused on right now. Anybody have a guess why I would be focused on that edge HJ? Yeah, because it's forced, you have to make it yellow because it's the very last edge incident to H. So we'll go ahead and make that guy yellow right there. Okay. Now, remember what we've got. We still have G is only incident to one colored edge. H is done, F is done, B, C, A is done. So we really only have what? D and E to look at that are incident to one colored edge, J and I to look at only incident to one colored edge, and G. Okay? So we got to figure out what to do with those edges next. So do you guys have a preference on who we look at? You said G. All right, so if we look at G, because we're starting to come down to the end here, we've got to be a little bit strategic. And actually here, it doesn't look like right now it matters whether we, well, it is going to matter. So let's check. At G, the edge coming out G to J and G to I has to be an edge that can be incident to a blue colored edge and a yellow colored edge. Do we have a color that we can deal with that? Okay. So that works so far. We may still get into issues, but so far it's working. Now, when we look down here, E to J is no worries, but what's up with ID and DE? Oh, no. Yes, you're totally right. That's the problem. Big call. There we go. We'll remove one of them. Whoops. So in terms of this edge G to J, suppose we had colored this guy right here yellow. Okay, so let's do that with the other one that I just erased. If we color G to I yellow, what's the problem with that? Well, then it would be incident to this edge that's already colored yellow, the F to I. So I'm going to strategically uncolor that one. Okay. Now let's keep going. So far, once we got rid of that one, and we're going to cross our fingers that we can deal with it in the future, we may be able to do something with these other guys. Now, a little further back, did anybody say it? Yeah, somebody said it about D and E. So if we look here at D and E, what does that guy have to be colored? That one is forced. Yep, that one is forced to be blue. And if that was forced to be blue, we would then force D to I, and somebody's talked about D to I. What are we now forced to color for this one? Yep, that purple color. Now when we go up to these other two remaining edges, and it looks like we've only missed two edges right now, what's the issue with those two edges? Anybody spot what color we need for those two edges? Yes. So it turns out we do actually need a fourth color for this particular vertex, not vertex, this particular graph. So I'm going to pull out the green. I didn't want to, but it happened. So both of those two vertices can be colored with the green right there. Now, if you tried to recolor this graph, and we totally could, but I'm not going to do that for us today just because we need to get through some more examples. You can actually, and I believe I've done this in the past, get it down to where that fourth color is only on one edge, but it does turn out that for this particular graph, there's no way that you can reorder it and choose the colors on the edges better than what we did so that you don't have the fourth color. So it does turn out that in this particular graph, your edge chromatic number for your Peterson graph does turn out to be 4. And part of that is just you had to have 3 colors on the outer cycle here, so you had to get that 3 right there going on. And then when you started coming in, the way these guys snarled, in the middle with that star-shaped, you just couldn't get rid of needing that fourth color. Okay? So that would be dealing with what this edge chromatic number is. Questions? Make sense? Kind of feeling okay? And just like with when you color the vertices, you can always use more than 4 colors, that's no problem. But if you want the edge chromatic number with the fewest number of colors, it would be 4 in this case. Yeah, where do you want to look? Definition of these guys or somewhere before then? Now, in reality, whoops, I moved my mic real quick. In reality, while edge colorings can be extraordinarily helpful, realistically, we have a tendency to use vertex colorings more. Okay, so I'm just going to do that one example of the edge coloring. Although you do have, I think, 1 or 2 of them in your homework. And notice you're just coloring the edges. All right. So this next example is an example where you would use colorings specifically to help you solve a problem. Okay, so this example I shamelessly stole from one of the exercises in your textbook and then updated it because it was dumb the way it was written. Okay, so here's what it's got. The situation is you're at some sort of zoo. They've decided to have, instead of all of the animals in their own little areas, however they've made them, so they've decided to have it so that they have multiple animals together in the same enclosure. Okay, so they're going to go and they're going to build these large open enclosures. And here's the only issue. They don't want their animals to get hurt. So they don't want incompatible animals in the same large enclosure. Where incompatible animals are, one of them would eat the other one in some way. Okay, so for example, we're not going to put, I don't know, something like, what's something that likes to eat things? A large cat with like a deer or something. There you go. A cheetah with what? We often see antelopes or something. Yeah, maybe you don't want to put lions and zebras together. You guys got the idea. Okay, but if you put a monkey and a zebra together, that would probably be fine. Yes, and definitely animals of the same type together totally would be fine. You got it. So here's what the actual question is that we want to determine. So the zoo wants to figure out how many of these enclosures they need, and because they don't want to spend an outrageous amount of money, they want to figure out the fewest number of these enclosures that they can make so that they still have all of their animals at the end of the day type thing. Okay, so what we're going to do is we're going to use a graph to model this situation. Now, when you use a graph to model a situation, you always have to determine who are going to be your vertices, who are going to be your edges, and I'm going to claim in this case we're going to do a coloring. We're actually going to do a vertex coloring to help us out with something. So anybody have a guess on what we could have the vertices, edges, and then the coloring represent? And this is specifically for a vertex. just because we just didn't edges. Yeah, there you go. So your vertices could be the type of animal or the species. I'm just going to write animal because I'm lazy. Edges, yes, I like the who eats who. I'm just going to use one word, so I'll do incompatible because that was the stupid word I used before. And so that's the PC way of dealing with who's going to eat somebody else. All right, and colors. Did anybody do guesses for colors? Yes, so we could do colors for the enclosures that we want to have. So this here would be the different enclosures. Whoops. All right. Now, once we have that down, we need to know what animals are actually here. So, let me move this up so we have a little more space at the end. Suppose the animals that we're going to refer to, and I realize that this is in no way, shape, or form all that accurate to an actual zoo. They would have way more animals, and things like small lizards probably wouldn't be put into something like this anyway. But suppose we're looking just at these guys to make our graph somewhat manageable. Okay, so if an actual zoo did this, their graph would be much larger than what we're about to build. So suppose they had tigers and elephants, lemurs, antelopes, storks, cheetahs. I just came up with a random number, some random animals there. If you guys want, we can put in some extra ones. You guys want me to add extra ones, or are you guys happy with these animals? All right, so I won't adjust this. Now, what I will do is instead of writing out the full names for all of these animals, let's label them. And one of the things I did when I came up with these names, besides just doing some random animals that I thought of the last time, it's been ages since I've been to a zoo, was I strategically picked animals whose names started with a different letter of the alphabet. So tigers will represent with a T, elephants with an E, lemurs with an L, antelopes with an A, storks with an S, and cheetahs with a C. And I'm going to assume we can figure out if there's some sort of incompatibility with these guys. Okay, the first thing we'll do the edges, and we'll go ahead and label all the edges with those letters. So it doesn't matter where I put them in. Graphs, you know, you draw it slightly different. It's just an isomorphic graph. So we've got T, we've got E for elephant, we've got L for lemur. Actually, let me put it in a rough circle. That's probably smart. A for antelope. And our edges is going to be who shouldn't be in the same pen with each other. S for stork. And C for cheetah. And I on purpose made each of those vertices open so we can color them. Okay. So if we want to put in an edge, where would you guys assume an edge would be? I would agree with that. So we should definitely have some edges attached to our tiger vertex. So let's check it out. If we look at tigers, should we put an edge between tigers and elephants? I don't know. Elephants are pretty big and pretty chill. I think they're okay. I think we can probably go ahead and say no edge here. We already said that the tiger would try to eat the lemur if possible. What do you guys think? Should we have an edge between tiger and antelope? Oh, definitely, definitely. Should we have an edge between the tiger and the stork? So we're going to go with a, we're not going to worry about it. All right. So we'll go ahead and put in the edge for stork. Oops. And what about tigers and cheetahs? Yeah, I'd say they're probably good too. I think those guys actually in nature overlap in territory, so I haven't heard of anything, but they're probably okay. Let's assume for the sake of this example that we're okay. Okay. So then we move on to elephants. So what do you guys think? If we look at this in terms of elephants being problematic to anybody, do we think elephants are probably okay? Yeah, I would agree with that statement. Elephants are probably pretty cool with being in any of these different enclosures. Now, if we move on to the lemur or the monkey, we're probably not going to have to worry about the lemur or the monkey eating any of these other animals, but do we have to worry about the lemur being eaten by any of the animals? Nope, we already had the edge between the lemur and tiger. Yeah, I would worry about the cheetah as well. So one of the ways that you can do this is if you're worried about your animals getting eaten or not working out with each other, is you actually go for the animals that are the stereotypical predators or actually are the predators. And in this list, I would probably focus in on the tiger, who loves stalking his prey, and ditto for the cheetahs. Okay? The other ones, they probably would be pretty chill regardless. I mean, you'd have to worry about the storks and fish, but we don't have fish on the list type thing. Okay? So I'm going to go ahead and skip out on looking at the antelope unless you want to look at the antelope with who would eat it. I'm going to skip out on focusing on the stork here unless you want to look at who eats it. And so if we focus in on the cheetah, who's our other predator in this list, what edges would we need to have an endpoint with a cheetah? Anybody got guesses there? Yeah, I would recommend putting in the additional edge. The cheetah potentially would eat the antelope. Let's not say potentially, would. And the cheetah probably would look for the stork as well. Okay? So look through that, see if there are any missing edges. All right, I'm not seeing any missing edges here either. So in this particular case, we then look to see if we can color this graph. And since I screwed up on the graph down there at S for stork, let's actually use a color that's different than shading in and not shading in. Okay. So if you start coloring this guy, you focus in on whoever it is that you want to focus in on. Maybe you focus in on the ones with the higher degree. Okay. So if you focus in on the tiger, then immediately, what do you know about other vertices in this particular graph? What are some colors that we have to worry about? And I just picked blue for our second color just because that was easy for me to grab. So who should we color blue, in other words? Okay, so definitely don't color sea blue for the cheetah, but yeah, you'd need to go ahead and color the lemur, the antelope, and the stork. So all those ones that are incompatible with the tigers, we'll need to go ahead and color them blue. And that then forces, if we want to use as few colors as possible, what should we color our cheetah? What should we color our vertex C? In other words, can we color that vertex C yellow? Yes. Now, just based on the edges, do we have anything that tells us what color we should color our vertex that represents our elephant or our vertex E? We don't. It turns out it doesn't matter. You could color it either blue to go with the non-predator animals, or you could color it yellow to go with the two large cats. And since it doesn't matter, do you guys have a preference? Do you want me to color the vertex E with yellow or with blue? That works. So if we go ahead and color that guy blue, notice what happens. This would tell you that the answer to this problem would be what? How many enclosures should this zoo actually make? So this tells you that since we have a two coloring, since this is a two coloring, because the colorings represented the enclosures, it tells you that the zoo should make or create or build or contract out to build two enclosures. If I could spell enclosures once today, that would be awesome. Okay, so that would be some of the ways that you can use these graphs, is they are literally a way to model the information that you have without going insane and still getting all the information. And yes, it is turned out to be a bipartite graph, but in the grand scheme of things, based on what we actually needed at the end of the day, extra information. Okay. Although having only two colors, so they only have to make two enclosures, I'm sure made the zoo, if this was a real zoo, would have made them happy. Okay. So questions kind of make sense so far. All right. So that is the last example that I've got for us in section 2.3. So let us jump now to our next section for the last little bit for today. Okay. So section 2.4, which is our last section we're going to cover in chapter 4, is dealing with two things. We mentioned this earlier today. It's going to deal with some theorems relating to colorings, and then we're also going to talk about chromatic numbers. Okay, some of these theorems, which are just facts about our colorings, we've already actually talked about. The first one we have not. So let me give an example of what this means. So theorem 1 says if you have a polygon, and this means the following, okay? So this is a graph that looks like some polygon. So maybe it looks like this guy. I'm just arbitrarily putting in a bunch of edges. I'm not making it awesome. Okay? So I suppose that's our graph, which actually kind of looks like a tree. Okay? Notice what this means in terms of the actual official names. This is the same thing as looking at one of those cycle graphs that we looked at last time, where it's just a big, fat cycle, maybe though it doesn't look like a circle. Okay? Maybe it has some funky shapes going on. Now, if you actually create a triangulation of some polygonal shaped graph, then the claim here is that it can always be three-colored. Okay? Now, the thing we want to know is what in the world is this triangulation? Don't overthink it. It literally means we're going to throw in a bunch of triangles. Okay? So a triangulation would be something like throw in those extra two edges to get things that look like triangles. Throw in extra edges up here that basically so all of your faces are degree 3 is another way to say that more properly. Is this the only way to do it? Absolutely not. But by throwing in those extra lines, or those extra edges, notice this is considered a triangulation because we see visually all those little triangles. But for a little bit more proper, we've got a bunch of faces, and all of the faces are degree 3. I should rephrase, all the bounded faces are degree 3. The unbounded faces have the same degree as whatever the number of edges were in the original polygon. Now, the claim here is that this guy can be three-colored. I'm not going to prove it. I'm just going to do it with an illustration. So let's see if we can't three-color this particular graph. So if we picked on some graph right here, okay, what would happen? Well, there's two vertices adjacent to him. So those two vertices have to be a different color. So maybe that blue and that horrible purple again. Okay. So then make sure you go to a vertex in the graph that is adjacent to some colored vertex. So maybe you pick on this guy up on the top. What color does that guy on the top have to be colored? Now, when we come down to this guy here at the bottom, what color does this guy here towards the end, where if this was a tree, it looks like the leaves and trunk of the tree are together? Anybody got a line on what color that guy should be? Yep. And at this point, we've got a lot of possibilities. Maybe we come back up here at the top. That doesn't have enough. We shouldn't do that one next. How about we do this one down here? What's this other guy that's sort of in the middle of the graph look like it has to be colored? Yep, it's got to be colored that purple color. Now at this point, if we go back up to the one that I wanted to do a second ago, this one is forced to be colored what? Blue. Then we can look at, how about this guy? Sort of in the middle again, but more towards the right-hand side. It's forced to be colored what color? Yellow? Yep. And what about that last one over on the farthest right-hand side? What does he have to be colored? This one right here. Yep, purple. And then there's two last vertices at the very bottom. So these two guys right here. So let's do this one first. It's on the right-hand side. What does that right-hand side vertex have to be colored? Yep, it's got to be colored yellow. And last vertex in the graph, what does the last vertex in the graph have to be colored? Have to be colored that horrible purple color. So now notice the strategy of what we did. The first one, we colored any random color that we wanted. the two vertices adjacent to this very first one could be colored two other random colors. But after that, there was always at least one vertex that we could strategically grab that was adjacent to two other colored vertices. And what happened? We were able to go around and color all of these guys with only 3 colors. So if you are able to notice that the graph that you have is a triangulation of a polygon, in other words, all of the bounded faces have degree 3, you are guaranteed to have a 3 coloring exist using this same strategy, okay? Kind of a cool little example, I have to admit. We're not really going to use this much. The only way that I would see this actually being used in our class is if you need to do a coloring and you notice that all of your bounded faces are degree 3. Okay. Now, the second theorem that we have here says if you have any old graph, lies, not any old graph, you do have an exception. The exception is you're not allowed to have one of those cycle graphs where it was a cycle and there was odd number of edges or odd number of vertices, and you're also not allowed to have a complete graph. Both of those are special cases, and this doesn't work. Okay? But as long as you don't have a cycle graph of odd degree, odd number of vertices, totally fine. But even number of vertices in your cycle is fine, but odd number of vertices in your cycle is not fine. And as long as you don't have a complete graph, it turns out that your chromatic number of your graph is always less than or equal to your maximum degree in your graph. That is a fun little fact, because notice what we had before. The criteria that we had before was the lower bound of the chromatic number was the maximum click size, but the upper bound was just the number of vertices. Now we can get rid of that upper bound being the number of vertices, and it's now the maximum degree among all your vertices. Please note the catch, though. Those two families of graphs do not apply to this new inequality or this new upper bound. Why? Because the number of colors you need to use is actually bigger than that. Okay. Now, theorem 3 deals with your edge chromatic number, and this one actually does a similar inequality. Okay, so for this one right here, notice what's going on. I think I made the inequality the opposite direction for you guys last time. That's awkward. The edge chromatic number here deals with this guy. Oh, no, it's just a typo in what I was writing. I was like, wait a second, that can't be right with D minus 1. It's actually D plus 1. Okay, so in terms of this guy, your edge chromatic number is either the maximum degree or one bigger. Now, that's actually super nice because it gives you only 2 options in how many colors that you can use. Now, you still have to figure out what the actual edge chromatic number is of your graph, but it's far less options than over here with your regular old chromatic number based off the colorings of your vertex. Okay? So that would be the idea there. The fourth theorem in your textbook in this section 2.4, and after we have this fourth theorem, we then have a definition. We're going to be done with theorems for a little bit. So for this guy right here, the claim is that every planar graph can be 5 colored. In other words, you can use up to 5 colors on a planar graph. So watch out for this word planar. If you have a graph that's not planar, you may have to use more than 5 colors, but if you are a planar graph, you can always use 5 colors. Maybe you can use less than 5 colors, but you can always use 5 colors. So here's what this means. There's a couple of comments with this guy. This means that your chromatic number is going to be less than or equal to 5. So if we put this all together, whatever your maximum click is, less than or equal to your chromatic number, less than or equal to 5. And that typically is super nice with your planar graphs. Now, something to note about your planar graphs, so this is a recall about planar graphs. If you had a copy of K5 or K33 as a subgraph, remember it's not planar. So this is a subgraph of the graph G. Remember that means G is not planar. Okay. And that's actually one of the ways that people show that you could actually have this 5 coloring right here, because if you start looking in at these guys and all their twisty snarlness, if you don't have subgraphs that are configurations of K5 or K33, it means you don't have the extra complexity of those larger clicks inside of your graph, and that's where you can get down to this 5 colors. Now, it turns out 5 colors is relatively straightforward to prove. Your book actually goes through the details of how you can get to 4 colors, and it's totally dealing with those subgraphs of K5 and K33. Okay. It basically says if you have to use more than 5 colors, you're guaranteed that you have one of those 2 subgraphs, is roughly speaking what it says. Now, it turns out this guy is very famous. It's actually called the 5 coloring problem. You have an additional fact, and this one actually was a conjecture for years and years. People thought it was true, but nobody could figure out how to show that it actually was true until relatively recently. It turns out there is an additional fact, which is the 4 color problem. This one is, I don't believe, in your book. It's called the 4 color problem. And what it turns out is actually every planar graph can be colored with 4 colors. That one is crazy difficult to prove. And people knew for a long time, or they hypothesized for a long time that this was true, but they couldn't figure out why. One of the places where these 2 guys are used a lot is with something like that. Yeah, it was, they had to wait until computers were used with proofs, because it was something like they had to check a bazillion cases or something. I can't remember the details off the top of my head. But both of these 2 guys can be used straightforwardly, but they're also used a lot with duals. So we talked about how duals were awesome in the past. So one of the things that people have done, and we vaguely talked about it, but I didn't show a picture, that one of the things with graphs originally we're dealing with maps. Okay? And if you have some sort of map situation with this, what people would want to do is they wanted to actually color the countries where those faces are representing countries. Well, we have absolutely 0 results based on coloring faces. 0, literally 0, okay? So what people did is they would grab the dual, okay? And remember, for the dual, what happened? You connect all of your dots. Etc., etc. There's another one. In this particular case, notice, though, we don't actually care about the unbounded face. Why? Because it's not one that we care about being colored, because it's outside the map. Okay? So if we then look at the dual, and we only look at the dual here in terms of what? In terms of the bounded faces, that's probably why your book doesn't deal with the unbounded face. So I'll go ahead and put red for the unbounded face. The unbounded faces and their connecting edges would be those guys. The bounded faces are in black. The unbounded faces and their corresponding edges are in red. What is that, 3? So the only thing we need to color is the black part. Okay. So if we go and look at the guide, notice what we see if we try to do a vertex coloring on that one, we can see that, hey, we literally could have done a 2 coloring. There was no reason to color these 3 different colors because the outer 2 most could have both been blue. Okay. So that's one of the things of where this idea of, is there a maximum number of colors that we can pull down to be smaller than your number of vertices came from. It actually came from if you're looking at the dual of whatever it is that you're dealing with. Okay. Now, that all leads us up into the chromatic polynomial. And for today, since we're almost completely out of time, what we're going to get is the definition of the chromatic polynomial, and then we'll do all of the properties, results, and tons of examples with it next time. Chromatic polynomial right here. And actually, let me insert a little bit of space because that's pretty darn close. All right. So the chromatic polynomial of some graph is an actual polynomial that you build. Okay. So it's a polynomial in terms of k, where k is, in terms of its domain, is just some integer. It's typically going to be a positive integer, and specifically that k is the number of k colorings you can have. So the k is the number of colors that you could use in the graph. So even though people have a tendency to not bother with talking about what the domain is of k, in actuality, the smallest k you could ever be would be your chromatic number, and the largest your k would ever be would actually be the number of vertices in whatever graph you're using. So there really is sort of a domain attached to this k. Now, in terms of notation, the notation for the chromatic polynomial, there's actually a bunch of different notations. I'll stick to the notation that looks like this: capital P for polynomial, lowercase k, which represents your k colorings, and then which graph we're going to use is this G. The other really, really common one that you can see is this one, where the name of the graph is in the subscript. And then the variable k is actually where you would normally think of variables. So those are the two most common ways that you see the symbol for the chromatic polynomial, although if you look online, it has a tendency to be lots of other symbols too. Okay. So that we just talked about. So we got enough time to build the chromatic polynomial for one example, and so let's look at a very, very famous graph, or really family of graphs, which is the path graph. Now the path graph symbolically is a capital P with a subscript N. Yes, I know it's probably a bad symbol one to pick because of that notation, but oh well. So in terms of this guy right here, so the path is length 4 but 5 vertices. If we want to build our chromatic polynomial, I'm going to do a little bit of scratch work. Okay. So the very, very first vertex would be any color you want. So over here to the side, k equals the number of colors available to use. So that means over here in this first vertex, while I actually did put a color in there, that yellow to indicate we colored it, in actuality, if we have k colors we could pull from, it doesn't have to be that yellow. It could be any of those k colors. Okay? Now, the second color, your color B, or the color you would color vertex B, can this guy be yellow? Is that allowed? And hopefully you're all thinking to yourself, no, you have to use a different color. So what does that mean? Because you're not allowed to use yellow, you only have k minus 1 of those colors available. In other words, not yellow. Okay? Now, you guys tell me, how many colors do you think are available for us to use for that vertex C? We're not trying to find the chromatic number here. We're just trying to do any old coloring. Right, so this would actually still be k minus 1 possibilities. Here, it's totally cool to use yellow again, but you're not allowed to use the blue. Any guesses how many colors we could use on vertex D? And then we're going to ask the same question about vertex E. So what do you guys think? How many colors are possible to use on vertex D here? Still going to be k minus 1. The only one you're not allowed to use now is yellow. Maybe you actually pull out one of these other colors. Maybe you don't use blue. This will mean that this is not the smallest number of colors possible, but that's okay. And then for the last one, it also turns out to be k minus 1. The only one you're not allowed to use is you're not allowed to use that purple that was the vertex adjacent to the last one. Okay? Now, putting that all together, here's the deal. The chromatic polynomial of this particular path graph, so notice I put in the symbol for the path graph inside the parentheses, is this. Anybody noticed how I got that polynomial? Well, you guys are thinking about how you literally just multiplied all those factors together. That one's not purple, and this one here is not yellow. Now, here's the deal. You can what this polynomial measures is it measures how many different ways there are to get a k coloring. So if you tried to plug in k equals 0, in other words, you use no colors, when you plug that into this polynomial, you'll get back a 0, right there. And so that would tell you, nope, you can't color it with no colors. If you tried to put in 1, k equals 1 for a 1 coloring, you'd also get a 0. So that would tell you, nope, there's no way to color it with a 1 coloring. But if you plugged in a k equals 2, which is our chromatic number for this particular graph, this gives you that, what? 2 times 2 minus 1 to the 4th. This tells you that there are 2 different ways to color this particular graph with 2 colors. You could do yellow, blue, yellow, blue, yellow, or start with the blue instead of the yellow. Okay? So that's what it's talking about, one of the ways of dealing with this guy. But we'll have a whole bunch more examples. We'll probably start off with this example again, and then we'll go on of other ways that we can use the chromatic polynomial and what all the different things this polynomial actually tells you. All right, but that is it for today. We'll pick up with chromatic polynomials next time. That's roughly speaking the only thing we have left in chapter 2.